Hello, everyone, and welcome to Handmade Hero, show where we code a complete game live on stream. We wrote the KD tree traversal code yesterday, the actual code that we think we want to start debugging. And so today, our job is to actually put our KD tree into the format that code wanted. It was a bit of a Snuffleupagus-oriented programming situation, which, as you know, I highly recommend, where we basically said, let's write this routine imagining that the data format was exactly what we wanted to make the routine fast, or at least as fast as we could think of at the time. And so now our job is to go actually make it in that format. So I'm going to go ahead and get started on that, because until we have a routine that builds the tree, we can't start debugging. And unfortunately, yes, this does mean we have to debug two things at once, because we both have to debug the tree build and debug the raycast. But, you know, at the very least, we should be able to get something running today where we can say, all right, you know, it's not debugged yet, but everything's in place for both the build and the testing now, and, like, you know, it doesn't crash and so on, right? So we'll have like a working model, but then we've got to actually debug the logic of it, because there's probably things that we didn't think of or got wrong. Since it's a very delicate situation we're dealing with here, right? We're trying to get this, squeeze this down to the smallest possible size and instruction count. And I think we did an okay job. Like, it's not horrible even as it stands before we've really taken an optimization knock at it yet. So I think, you know, compared to this guy, it's probably going to be better. But, you know, like, we never know. So that's why we're going to have to see through actual debugging and running of it how it actually performs. All right, so what we need to do is we need to produce a version of Splitbox, and I might just leave the existing Splitbox in place at the moment and just write a new one. So, like, this is going to be called, like, SplitKD or whatever. And this one will just do, it's going to be substantially the same routine, but I just don't want to have to deal in line with making both of them. And so I want to leave the old one just for reference purposes, so we can still run it. And then later, when we actually have this one debugged and we're happy with it, if it is in fact faster, we'll just vape the old one and use this one. But I don't want to have them both operating in place. That's not my idea of a good time at this point. So we're just going to do this. And so we're going to come through. It's going to do exactly the same pass. We're not really going to change how we're building the tree yet, because I don't want to change the metric yet. So I just want to isolate. Like, it's like, just to put everything out there, we don't yet know if we could do a better job dividing our boxes up into KD trees too. So that's a separate thing we can improve. But right now, we just want to improve for a given KD tree. How good can we test that tree? That's what we're trying to do now. So I want to leave the metric exactly the same. I don't want to change anything about that. What I want to do instead is just go ahead and try to divide everything up the same way and see what happens based on the splitting. Okay. So one of the things that's a little weird about this though, even as I'm saying that, is we can't really do exactly that. Although I guess we sort of could, depending on how we want to restructure that routine. So, So here's an interesting thought. One of the reasons, like, one of the things we were doing before is we were allowing overlapping rectangles, and I hadn't really thought of that before, because if you look at this here, we don't go out of our way to ensure that we actually split anything, right? So we may have a place where we cut a box, like, literally in half, so it would be on both sides of the thing. And we could just include that thing on both sides if we wanted to, but again, that gets more expensive. So we could also do something where as we go down the KD tree, we just let the thing test each time. In other words, if we wanted to, when we look at the actual hit testing, so this here, what we could do is just make this be a while loop and have it happen every time. You know what I'm saying? So we could actually do that. And then this would just be its own if that's totally separate, right? And I guess I don't really know what to make of that. That's a really tough call because we probably would need to test it both ways to really know which one we should do. Because in one case, anytime you split a box, you are adding a check to either side. But on the other hand, if you do it this way, you're doing leaf checks possibly much earlier than you should. And so you may be wasting time with those checks when you would have found a much closer hit and never had to do them if they were actually placed into the tree. So that's a tough call. Gosh. That's a tough call, and I'm not sure which way I want to do that. I mean, my gut instinct says, look, you probably don't want to proliferate boxes, so maybe you would put this up and just always have the ability to check them. So they're basically loose bounds, and anything that can't be sorted into one side or the other comes up here. You know, that seems reasonable. On the other hand, there's a certain purity to saying, look, we only do this side of the branch when we get down to the bottom of the tree. That implies that, like, hey, a lot of the time you have less unpredictable branching, perhaps, right? Because now, instead of this unpredictable branch happening every time you walk down the tree, it only happens that one time. So I guess, honestly, I guess I might say, like, let's just split the boxes? Gosh. I'm really torn. Like, the other reason I don't like that idea is that I don't know if there's really much of a bound to it. Like, how many times are these boxes going to get split up, right? So let's see. I mean, let's just see what would happen here if I was going to change that aspect of it, right? So let's suppose that I did this. So in here, when we come through this part of the routine, let's suppose I did something more like this. So I said, like, all right, while leaf index is less than one past last leaf index, then do the thing, right? Oops. So, maybe it goes through and it does that so that everyone, if they want to, can have leaves in them. And then in here, we would just say, okay, if we cannot go any further down the side we're going down, then we stop. And that would just be something we would test, I guess, separately, right? So I'm trying to think how we would want to do that exactly. Because it means we would probably want to store one additional bit, right, that just says, do you keep going? And we would look at that. So we'd come through here, we'd do this loop on all of the things, we'd test all of the things we have to test, right, to produce a new hit for this region. And then when we get down here, we would do we would just need to know if this thing has sides, right? If this thing has sides at all. And I guess what we could say is the sides, if a side is literally 0, then it doesn't exist, right? So we could just test that, right? We could just test that. In other words, if whatever the KD thing was for this, when we look it up, like we're going to go grab the curstack value here, right? So you know what? No, because we stuck the curse. Yeah, so no, that won't work. The reason that won't work is because the curstack value there is what is used to determine the leaf index in the case where we. There we go. We actually just use the same index, right? Because either it's referring to leaves or it's not. So that wouldn't really work. And to be fair, we probably could make it work because we have room and we know you have some extra, we've got first leaf index in here and I think we're currently not using it, right? So we could use first leaf index instead, and I almost want to say that's not actually used anywhere, right? Like, in other words, if I compile this code, let me just get rid of split KD here. There we go. So if I compile this code and I were to remove first leaf index, right? So that goes away. Nobody's actually doing anything with it, right? So we could actually encode the leaf and leaf count in there directly. And so we can do it the other way. It's just, yeah, I really wish I had an idea about this. I'm just really not sure which one to do. And I don't really want to have to write both, but all I can think of is it seems like you'd have to. Like, it seems like you'd have to write both and just see which one was faster, because I don't see much way of not doing that. I mean, right? So I want to say that what we probably let's just do it this way. So let's do it this way. Let's say in here what we do is we say, all right, so there's a separate thing called leaf index, right? And what we do is we say in here we're gonna do the leaf index from up to the one pass leaf index by doing the leaf index leaf count bit, right? And what we could do is just have both of these things be values. So presumably we could do something where we just say, all right, that's what we've got here. We don't save the leaf count because nobody cares what the leaf count is. And then what we do is in here, we just do a while leaf index is less than one past last leaf index. Then we do our loop. And then in here where we do like curstack value stuff, right? In here where we do that and we do our while depth bit, this is just going to be a different if statement. This is going to be if the leaf index is 0, right? Or sorry, it's the opposite way around, I guess, right? So, well, no, actually, I guess it's just whether you wanted to set it. It has nothing to do with the leaf index at that point, I guess. So, yeah, in here, the leaf index, one past last leaf index is just unpacking these. First leaf index. Because at this point, we still have it, right? Yeah. So I guess the problem we would have here is when we pack that, we would have nowhere for it to go. So we'd end up looking up the KD again. All right, I give up. I'm officially just going to say, look, you can't do that. You have to split boxes. So split them if you have to. It's not my problem anymore. Right? What was that if 0? Okay. So I'm going to say, yeah, we're just, because there's just not enough room on the stack at that point, and I can't think of anything obvious to do there, I think we're just going to leave it this way, because it's fairly compact this way and doesn't require re-looking up anything. So I'm just going to say that's what we're going to do for now, and then we'll look and see if maybe we need to do something else later. But that was enough for me to say, okay, we're going to start with one that isn't allowed to do that. All right, so let's go ahead and do split KD, and what that means is if you split a box, you've got to split the box in half along the KD axis if you can't figure out a way not to. And we can make this routine smarter so it tries not to do that. But then it sends it to either side. Right? So that's what's going to happen. So yeah, and again, one of the things we should keep in mind here too, like I said, is that like this is a totally stupid, in fact we should even put this here, like to do KC. This is a pretty stupid KD splitter. We should look for better fast metrics for picking the split plane, right? So yeah, I think we now just need to rewrite this routine and make sure that this thing splits in a way that we like. I'm going to probably rewrite this slightly. And the reason that I'm going to rewrite this slightly is because I want everything to be handled sort of in a more logical place without having to be sort of partially inline and partially not. So think of the first thing I want to do is say, all right, there's a KD index. And what I want is the KD index to start off, it's an axis. I want the KD index to start off saying no split. So a KD index of 3 is like, it's not split. This node is not a splitting node, right? Then what I'm going to go do is say in each of these, we're just going to record what the split actually would be, and then we're going to do the split later, right? So in here, whatever this, whatever this classifying is here, we're going to let it happen twice for now. And again, this is just to try and keep the complexity down for a little bit. And we can worry about building these quickly later on. So I'm not sure. I'm not sure if we really need to do much other than say, okay, so this. Yeah. All right. So going through here, you can see the counts, like count A and count B, right? And in this case, we're basically saying, look, if this was a split that we're going to use, then we'll just break out, and I'll call the KD index. So I'm literally just going to copy this exact thing and say, for now, we're just going to do it this way. If we found a reasonable split, we're going to split, and we're going to record which one it was, right? So here's the dim index, right? And we're just going to record that dim index, right? And that's the one we're going to split on. Then in here, we can basically say, okay, if the KD index equals 3, then we know that we did not split, right? So this is actually split false. And otherwise, we know that we did actually split. And we can also assert that the KD index is greater than or equal to 0, and the KD index is less than or equal to 2, when we get in here, because it has to be one of those, it has to be one of the dimensions we actually know about. So next we would basically say, okay, let's move into the body of this, the thing that actually does the split. So this is going to be in here, and this part here is the non-splitting part, right? And these will have to get rewritten because they're not doing what they should be doing at the moment. So we also would put this in here, right? Okay. And so now what we need to do is think more about what the actual stuff we need to write into these, into the sides section actually contains. So we don't really know how that's going to work yet. And the only way we can know is to go back and reread our routine and see what is the actual information it wants encoded in there specifically. So when it comes through and tests one of these things, what it's going to do is it's going to push onto the KD stack some piece of information that it received, right? And then it's going to unpack things like the leaf count and like the node index, like that sort of stuff that it needs. It's going to unpack that. And things like the plain D, that sort of thing. So inside those sides, we need two things. We need to pack our plain D and our KD index. And then we need to pack our child's node index and our child's leaf count. And the node index will actually be the leaf index if this is a leaf node, right? So what that means is that this routine definitely gets a little more complicated, because what will actually happen here is this KD tree node for the sides, that needs to not be passed in anymore. So what's actually going to happen is when we do this whole garbage experience, we don't actually want to create a container node until we actually think we're going to split this thing. And then once we actually split it, we need to see what the sides say we should pack, right? But we don't actually want to have one of those at the start, because if we don't, so if we're on this side of things, then all we want to do is pack these up like we're doing here and then ignore all of this. Like none of that wants to happen. And instead what happens is we have like a result parameter that we pack back. So we're going to do like a pack, and we're going to send it back to the other side, right? So here you can see us passing back the plain D and then the sides information, right? So what we essentially want, and now you can start to see the shape of this routine more clearly, is there's going to be a return value here that's like, oh, and actually split is now irrelevant. There's going to be like a pack value, right? And the pack value is going to get returned to the parent because that's what they need to put in their side array, right? So now it seems pretty reasonable. Like this all seems fine to me. So in here you can see what we would need to pack is we need to pack the leaf count and the node index. And obviously we're always packing in the KD index pattern and the plain test pattern. So the KD index pattern and the plain test pattern always get packed in by the parent. So in here we only need to pack the leaf count and the node index, right? Yeah. So since those packs will actually always be the same, I want to say, we can probably do this a little bit differently, which is to say that in here we can produce the pack value in one stable location, and then we can deal with the packing by saying, look, here's the node index to pack, here's the leaf count to pack, right? And so in here we know it's source count, so leaf count equals source count. Ah. So we know there's a safe truncate to U8, so we're going to source has to be packed, because we know that if it's greater than 4, we're going to try. We want to watch to make sure that we actually split anything, I guess. I suppose in theory, I wonder if this is a problem, because in theory we could get into a situation where we actually can't split, and I don't know what we do about that. If you have a thing where there's actually 256 things that cannot be split along any dimension, but how would that ever happen? I don't think it could. So I think we're okay with that, but we would want to know, right? The worst that would happen is you get wrong raycasting, so I think it's okay. But anyway, so in here we would say, all right, we've got our leaf count all set up, so this whole thing will just work. And the node index is just whichever the first one is. So I guess I shouldn't, I was a little hasty there. Where is that? Is that bit in here somewhere? Oh, what am I thinking? We have this routine copied just right above. So where is my split box? There it is. So we want to do this as well, right? So this needs to happen to add the box storage, and then we need to know what the node index was, because we're going to pack that, right? So there's our entire set of information along that path. I think that's just correct, right? So this looks fine, and yeah. And then we're all good. It's just, this is node index now. And then we're just down to the other side. So in here, where we actually do need to, we need to add a KD node in this case. And then we need to go through and actually do the classification. And this is going to be a worse classification, actually. We're probably going to need to change exactly how we do this, like I said. So we're going to change how we do that. But for the time being, we're going to have to add a KD node here, right? And then we're going to have to construct the KD nodes. Contents. And the difference here is, I mean, we're still effectively doing the same thing, but the difference here is we're going to have a thing that splits boxes in half and puts one in one side and one in the other. So that's the real, like, the main difference we're going to have there. So we probably will still have something that looks roughly like this. It won't create child boxes. So this part is not, this is not going to happen, right? So none of that happens. The KD node gets added here, and I guess we want this to be also like a node index, because we're going to need to know it. So our KD node index here, or this index, this node index, I guess we'll call it maybe. We're going to add one to that. And then we're going to go ahead, and we don't ever add them anywhere else. So actually what I more would probably do is say this node index equals solution KD node count plus plus, right? And what we would have to do here is say, like, look, if the solution KD node count is less than the total number that we can ever have, right? And we don't know what that is. Then we can do this. Otherwise, we just return a PAX value of 0. Because we would have to, because we can't build any more of the tree. And that's fine, it just means inaccurate lighting for that frame. So that's good, because we don't want to, like, crash if the lighting can't happen, right? We just want to have bad lighting. So that is also good, if we blow out the bounds at all, right? So I think this is what we'd do. We'd say, all right, let's get a node count here, update, then let's grab that particular node. So that's this node. I might change this and say this is the pack node index. Although they are the same, so no, I guess I would just call this node index. I mean, it's what it is. It's what we're going to return, right? So that's the node that we're actually going to use the next time around. And then when we get down here, like I said, we sort of have a little bit of work to do with the splitting. So in terms of splitting, this all needs to get rewritten. But what we do know is that we're going to effectively have a pack value. So this is side 0 pack. So what we're going to do here is, I guess, this, right? So this is like the negative sign pack, and then we're going to have the positive sign pack like this. I guess, I mean, it probably should correspond to the bit. So maybe it's the other way around. I don't know. That part doesn't really matter because we can choose whichever way we do that. And we just have to make sure that we're picking the sides the same way in both places. So which way do we do it up here would be the next question. Here we go. So up here we say, let's move the mask in terms of what we saw. And then we're going to say descend down the start side bit, not the inverted bit. So I guess it's like positive would be 0, right? And negative would be 1. So it's the sign bit is what you use to address into there, right? So then in here, this part, again, is not really relevant to us. So I'm guessing we would do something, because like if you look at what's in here, we need to know the plane D, right? So we need to know this. And we need to know the sides. We need to know the first leaf. Well, no, we don't, because that doesn't exist, right? So the first leaf index. So now that I think about it, actually, do you need any of these things? Though? Because do the sides just always tell you that? Like, couldn't we have just packed that into the sides? I mean, yes. So I don't think you need any of this. I think this is all a waste of time. Right? So I don't know that we need any of that for anything. The first leaf index, the leaf count, and the KD index can all be packed into the side. Because by definition, it has to be, because we then count on it being packed into the side later. Right? So, I mean, if I look, I think it's just literally like you set the plane D here, and the plane D is set to whatever the heck the plane D was set to. So it's like this thing, right? The classifier distance. So this is the plane D here. And if we go down to this, we would just say, all right, that. So once we set up the plane D here, all we would do is say that once we know that, we don't have to do anything anymore. It's literally just this. Because everything else we would pack into these sides values, right? So, yeah. pretty sure. So I would probably prefer to do it like this. Where we accept the node index leaf count pack back like so. And then we OR in like, what's the stuff we need? The index and just the index, right? So we pack in here our KD index. So this is our like KD index pack value. And that's just this thing shifted up, right? And so thinking about that, like if I'm thinking about that, which I am, the way that we decided to pack the KD indexes into this thing is they were just shifted up by 28, right? So it's just like slammed on the top of that thing. The plain test pattern, and I guess we could put the plain test pattern in there as well. Because it needs to be, right? So the plain test pattern is just whether it's the positive side or the negative side. Oh, and that's different on either side, so I don't know why I would do it that way. So this is the positive side, and then this is the negative side, right? So the positive side, plain test pattern, and the negative side, plain test pattern, are these things. They are 24 bits up, right? And what I need to do is just have whichever pattern corresponds to the correct side. Now, if those are the sign bits, then all zeros is the positive side. So it's actually just 0. And if it's negative, then it would be all ones, right? So we have all zeros are all ones as what we would actually use for ORing things in. And that's it, because the plain D gets put in separately at push time, because there's no need to store it, since when we push it, we have it. So we can just, you know, get that. We don't need to store 64 bits. It just bloats the structure. The KD index gets packed in here, the plain test pattern gets packed in here, and the leaf count and the node index get packed right here. So the node index or leaf count, all we need to do is shift these up. So it looks like the node index is shifted up by nothing, and the leaf count is shifted up by 16. Right. So that's the complete pack. Like that's it. So what I need to do now is have some conceptualization of the maximum number of these that you can actually have. Right, and I guess probably we'll just make it be the maximum that there is. So basically, like, we'll allocate a full complement of that because that space is pretty cheap for us. If you imagine we have 65536 of these structs that are 12 bytes each now, like, it's less than a megabyte of scratch space, which these days you're lucky if you can get, like, the DLL for one entity in your Unreal game to be less than 1 megabyte. So, like, I'm assuming we can probably just say we can afford maximum scratch space there, because we don't care, and we won't touch it. It won't be cache pollution if we never touch it. So only if you actually stressed it to that level would you ever actually pay for that. So I think that's fine. Now the problem that we're going to have immediately hereafter is that now we don't actually know. Looks like also next dim index. So next dim index is actually something we would have to produce outside as well. So in here, I would say we probably just do that. And that. I don't know if this is actually a good idea anyway, but something like this. Okay. So yeah. So now I think we're all good here. KD node count should be fine there. What's the actual problem? What is that actually complaining about? Does anyone know? Oh, previous declaration. Yes. Sorry. Thank you, compiler. That was not intended. So I think now we're more or less... This routine is more or less correct. And what we need to do now is write the code that will actually break... Like, that will split these things up. And I'll be honest with yous, I don't really know what we want to do here. So I think I think this is an open area of research for us that we want to probably play with later to see what the way is to build the most balanced KD trees we can. And we weren't doing that previously, right? I'm going to keep, like I said before, the way we're doing it now just because... since I don't know, and you know what, let's just pass a rectangle 3. Since I don't know yet how I want to do that, and I want to compare apples to apples as much as possible, we're just going to keep doing it the same way we were doing it before. So here I'm going to say, like, look, let's do a get center on this thing. So we'll just use the total bound center here, which is what this was computing. And then I think the classification system would just work. And then when we come down here, this is only this part actually has to get redone. And the reason this part has to be redone is not because we couldn't just use these counts that we produced up here, but rather because we actually need to look at the splitting properties of this. Right? So... yeah, like I said, not exactly my favorite thing in the world. I don't care about ref.ca, ref.cb. Those are not relevant anymore. Those are color approximators we were using for long-distance raycasting, and we're just not going to do that anymore, I don't think. So, and we can, you know, and it's cheap to add it in. Either way, we wouldn't do it here. So in here, what we want to do is we want to do substantively the same thing, but now what we need is something that's more like if it's clearly on one side, we do one thing. If it's clearly on the other side, we do the other thing. If it's split down the middle, we add it to both sides, right? So this like check approximator thing is fine. We can leave it that way. But then what we need to do here is when we do this, sort of when we brush through here, we would need, and bounds A and bounds B, by the way, are exactly what we would pass to this and this. And let's do positive bounds, negative bounds, and then like negative count. That way we can see what those are, and we don't have to remember what's A and what's B, because, you know, you could see screwing that up pretty easily. So we'll just do positive counts and negative count, and we'll do it that way. All right. So I think that's all fine. And all we need to do now is in here have this be like 3 ways. So this is going to be like if add a, or if add positive, and if add negative, right? And we might sometimes set both of those things to true. So we would do this and this. And here we'll just say positive count. Here we go. Positive count. Negative count. And here we would do negative count. Right? Looks like we're doing a forwards-backwards build there, right? And so here again, just changing the names of these, is going to be positive bounds and negative bounds. And this will be positive bounds and negative bounds. Negative. Positive. When we do the rect min max here, that is just, we're going to need it, so we might as well do it here as box bounds. And we probably just should have made that be a rectangle. Doesn't really matter, but whatever. So then this is positive count plus plus. And this is negative count plus plus. And now we've got a proper summation for these. And so this is going to be like an else if else kind of thing now, where we do like add positive equals add negative equals true. And here it's going to be like add positive equals true, add negative equals true. Right? And so what we need to do here is we're going to do exactly the same thing as before. It's just instead of classifying the center, which is what we were doing before, we're going to classify whichever dimension of the box was the one that we actually need to check, right? So if we're checking for adding to the positive side, what we want to see is the minimum one higher than the class distance, right? So when you subtract away plane D, right, which is what we're doing here, right? If you subtract away the plane D from this thing, then what actually happens, right? And I don't know why we're even doing it this way. This seems dumb. I mean, that doesn't even make sense. I don't even know what the heck cluster is there for. This is just yeah, that's just, all right, whatever. So, I mean, this is just this. Right? I mean, that's what we're doing. So, if it's greater, we add it to the positive side. If it's less, we add it to the... Oh, actually, wait. No, we can just do this directly. So, what am I thinking? Add positive is just a Boolean value. In fact, we don't even need to store it, right? All you actually need to do is say, look, is the maximum value, the furthest it could be, is that on the other side? Then you're going to do this branch. And if the minimum value is on the negative side of the plane, then you're going to add the negative branch. And we don't need to do any of the stuff that I was just saying, so ignore all that. As Key and Peele said, forget everything I've said up until this point. So I think that's actually all we needed to build the tree properly. And why the heck this thing was written this way, I have no idea, because there's no need for a dot product. I guess we were thinking maybe we would use other kinds of planes at some point, but this is stupid, and we're not going to do it. So, like, this, yeah, it doesn't really make much sense to me. Right? Like, why wouldn't you just have done this? You know what I'm saying? So it really doesn't make sense why we would do that, and yeah, I just don't get it. So in this case, if we wanted to do this check still the same way as we were checking it before, we can just say that we're going to actually multiply it by this thing E, right? And then we just check it. So no more inner products being thrown around for no reason when we can just do an offset load. Yeah, doesn't matter. All right, so this thing will build our KD tree now, so we can just call it. And the problem we're going to have is we haven't allocated any space for it, so it's just going to crash immediately because we're sending it off into null land, right? And sending it off into null land is not a good plan. So we're going to need to allocate some space for it. But let's at least verify that that does happen and hope that it crashes. Because if it doesn't crash, that means it's not even running. Which means we've failed quite hard. Whoops. So anyway, in build spatial partition for lighting, you can see here where we've got all this kind of crap happening. What we want to do here is do a split KD on this thing. And what I'm going to propose here, because I have no real better idea about what we should do, is I'm going to propose that we now add a global control switch that basically says, look, you build one thing on one path, you build another thing on the other path, right? So the root box index can still be used. It's not really a root box index anymore, but, you know. We don't need this. We don't need it. We don't need any of that. But what we're going to do here is say, all right, there's a control thing here, and this thing is going to be like lighting, use old KD, and that's going to control both things. So, you know, you get whichever tree it is that you thought that you wanted when you set up the lighting system. And if this one turns out to be demonstratively like way better, then we just go vaporize the other one. And if it doesn't, we play with it for a little while to see if there's a reason why it isn't that is obvious. And if there isn't, then we just walk it back out and go back to optimizing the other one, right? Okay, so light, use old KD, blah, 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 whatever, and so on. We're just going to define this to be 1, and we're just going to verify that we can still build it that way. The box stack, KD stack garbage can also happen the same way. So we can do this, right? Where we define those two. And actually, that doesn't actually make any sense, what I just said. This is only used on this side of the branch now. So probably the right way to do it is just put it here. And this is only used here. Right. So, yeah. So that seems better, and you know, I'm happy with that. So now what we should see, in theory anyway, is if I run this under remedy, we should be able to run the old way and get it to. Okay, that's the wrong. I loaded the wrong program. So we should see the same results that we had been seeing, which right that does look. Right, and then if I run it the new way, it should crash, like I just said, because we didn't actually give it any space to work with. So I'm assuming it will just, you know, just die. This needs to look like this. And we need to pass the total bounds here. That was my little foot stamp. Did you like it? When we pass the total bounds here, we need to pass the occluder bounds. And then we need the solution root box index to equal the split KD, but we don't want it to have the leaf count in it, which should actually be fine. Because it can't, right? It can't be a leaf. At least I don't think so. Well, no, it could. What if you just had very little? Yeah, so actually, it should just be that, honestly. So that's the split KD, and where's the parameters of that thing? So it takes the solution, the box count, the source, the dest, the dim and accidentally deleted the dim index. And we want this thing. I'm gonna just call this like root KD value and put it in there because, you know, honestly, it needs to be there. And so then when we do the box at the start, what we actually want to do is just unpack that index. That way it'll work, even if we have some weird degenerate case where there's like nothing to light. So what we really want to do here is this, right? So these two values, the leaf count and the cur stack value, those actually want to come out of the packed value here, which is the solution root KD value. You know what I'm saying to you? That's not good. Thank you, compiler. That was a good catch. All right. So that's everything. We should now crash the first time we try to write one of these things. Oh, and you know what? Let's compile in debug mode because obviously the release mode's not going to show us much. We should crash like right when we first try to add one of these things. So we'll try to add it and it should just crash because none of that stuff's initialized, right? And that's exactly what we get. So that's good news. At least we got what we expected. So now let's go in and actually add the scratch space in so that we have some space to do these. So that's going to be an HH light prof. In the same place where it just allocates scratch space for everything else, like you can see here, right? We can allocate space for this. So in here, I can say, and I don't know where all this stuff needs to go. So it's KD nodes, right? And I mean, I guess I could just put like 65536 in there and call it a day. But I'm not sure if that makes the most sense. Maybe it does, maybe it doesn't. For now, I'm not going to do that. So for now, I'm going to say, all right, let's get those KD tree nodes in here. We're going to malloc a uint16 max times the size of one of these KD tree nodes. And off we're going to go. Now, that's going to be too much space at first, I believe. Also, let me just run this and see what happens to us. So it looks like we spiral out of control. So just Stack Overflow there. Not the website, but an actual Stack Overflow. So we're not getting KD index equals 3 hardly ever, it looks like, for some reason. And I'm not sure what that reason is, but I guess we'll find out in the future. So we'll look at that later. What we're going to do now, though, before we do that, before we do anything else there, there was one other thing I wanted to do, and that was remove the cruft that was in this. So I want to say all that can go away now, right? Am I right about that? So if we want to get rid of that KD index, which we do, we need to remember it, right? So we would need to do this. want to make sure I'm thinking about this correctly. So I'll be honest, I don't know that I'm right about that. So when you first test a value, right, you need to know what the KD index is of that thing that you're testing. And up here where you push on the opposite side, you need to know what that KD index would have been. So you would need two KD indexes here, right? Because only the plane D is told. So you'd need the KD, you'd need your KD index, and you would need the KD index of your of the next person down. Now, honestly, that's probably fine. Like, you could do that. It would look like this. Right? Yeah. So it would look like this. And it would just unpack whatever the KD index was. And at that point, I think we actually filled the entire 32 bits with stuff. Right? And so if we wanted to do that, I mean, I guess we just can. This is kind of a ridiculous routine. And I don't know if I'm being smart or stupid. Usually, it's very difficult to tell the difference between the two until you have runtime measurement of something. So I am totally unsure about which one I am at this point. So there's that. I got nothing. That's just what we're doing. This may be fantastically stupid. I need to work it. I don't even know if I'm in the right ballpark here of stuff. Like I'm really surprised by how that routine looks. And like I said, either it's very smart or it's really dumb. And usually, you unfortunately, it's the latter, right? Usually, if you're trying to be too clever, you are trying to be too clever. So I don't know. We may have to walk a little bit of that back as we start to step through it and realize, oh, duh, that was really stupid. But I mean, that's just the way it is. Nothing ventured, nothing gained. You know what I'm saying to you? So, all right. So now we should be able to start debugging this thing. And the first thing we need to debug is our split node, like this thing. Because that's not correct now, right? This is also smaller now. So I don't know how we want to document that cache line size because 64 divided by 12 is a weird number, right? So I'm just going to leave that off and pretend we didn't think about it. And just say it's 12 bytes. Aren't you happy? I think we're all good there. So let's go ahead and debug our split KD node thing. Just let's double check that it's actually even plausibly doing something. So here we're counting values by saying, where is the total bounds, the bounds that we're looking at here? What's the center? And let's go ahead and take the counts of each of those, right? Now, what I would say about this is we probably want to just record the best. We probably want to do like something like picking the maximum minimum size. Like we want to do something where we actually test all three, because we don't just want to pick one that happens to have a count, but I don't know. I mean, well, like we might as well pick the best one because we're doing a second pass over it. There's no reason not to do that, right? Hard to say. Anyway, so the dimension, yeah, that like I guess I would say like you want the lowest maximum. Is that right? You want the lowest maximum value. Let's just do that. Oh wait, no. Don't do that yet. Because I said I wanted to test it apples to apples. So pick the lowest max value. We'll do that next. After we debug all this crap. So the KD node here, we basically say like, look, if we can add another one, then we do. And we add the node count here. We get the plane D. We classify everything as to whether it's on one or the other side of a plane. Oh, although I guess we should also assert that both sides got something, because they should always, presumably. Well, that doesn't really matter. We pack those up, and then we're off. Right? Node index. Leaf count stays 0 in that branch. Yeah, so I would have thought that would work. It obviously didn't. So we're testing to see whether the element is the maximum side of the box is on the other side of the positive plane, and the negative side of the box on the negative side of the plane. I guess the problem there is eventually you get down to something where you're not... Yeah, so I guess the problem that we're going to have is I can't not change this. Because if I don't change this, it's just going to always keep splitting potentially... Although, since it cycles the dimension each time, still should have been okay. I'm going to go ahead and just step into this. I'm not really sure why that's failing. So let's watch it fail, because I don't feel like I really have a handle on it, honestly. So let's jump through here. And I guess what I'll do is let me just let this thing go a bit for a while. So maybe I'll just like watch this part. I assume it breaks the first split. I'm assuming it breaks like right here. Right? Okay, so no, it doesn't actually. It has to actually get down into a cycle at some point. By the way, in case you're wondering, some things that don't work with Visual Studio is what I'm doing right now. Like, I loved that thing where I was like, wow, Visual Studio is really slow, and everyone was like, why do you need it to be fast? Can't you just use the data breakpoint? No, like, there's more things in a debugger when you want to watch your program run. I have so little patience for modern programmers. They drive me nuts. Their standards are so incredibly low. It's like, it's infuriating how low their standards are, right? It's kind of like, you know, they build like a house that's like 4 2x4s that are kind of all wonky, and then like a piece of canvas across the top that they like nailed in, and they're like, it's a house, and you're just like, what are you talking about? Have you ever seen a house before? Like, no, it's not. But they're like, nah, it's great. Why would you need anything else? If it's raining, you just go under the canvas part. Unbelievable. So this is, we've gotten into the loopback state now, right? Because I could see the stack kind of proliferate. So I just want to look and see what's going on now so that I have some understanding of the situation. So here's the positive bounds, the negative bounds, the positive count and the negative count. So I wonder what the box bounds actually are. So I'm going to step through here. So let's take a look at box bounds. Here is box bounds. Oh, so by the way, here is, I think I saw X13 pixels out there. And I was just lauding his debugger for saving us all from the collective disaster that's Visual Studio. I wanted to throw out a feature suggestion that I find I have a problem with a lot. And there is a thing in Visual Studio that sort of tries to solve it, but it sucks. It would be cool to have one in Remedy and make it good. So when you have something like box bounds, what I want to see is just a quick summary of what the thing is over here. And I feel like there's a lot of ways you could implement this feature, and I don't know like what the best possible way to implement it would be, but there's like some suggestions, right? So I think the ultimate suggestion is, can you just make a thing where in the executable you can just define like this, like and then like the name of the thing. So it'd be like that sort of thing. You know what I'm saying? So like basically there'd just be like a function, and then in here I can just serialize this thing like out to Remedy. Do you know what I'm talking about? Does this make any sense? So Remedy just looks, when it loads the exe, it just looks for any symbols that are like Remedy Watch. And then if I have that, I can just, there's like a button in here, like a preference setting, or like probably a button, probably a setting like right here, where it's just like, do you want to call those or not? Because sometimes you want that turned off because you're like, you don't want to be like re-entering that code because you're like debugging something in there. But then like other times you just click it and it'll just call you and you print out the thing. Does that make any sense? I don't know how achievable that is with the current way that like Remedy works necessarily, but just a thought. Because then if you could just get that working, you could do like anything you want here. And I wouldn't do this, by the way. I would probably actually do this. I'd make an H file that defines this thing, right? Because then you can also do stuff like, you know, requested size and pixel buffer and I don't know, right? Like you could imagine doing stuff where people can dump images out to that and waveforms and who cares, right? And like that would get you entirely out of the business of even having any of those features in Remedy if you just had the ability to take like bitmaps or strings and they get dumped out to Remedy and then people can just write these and you can even then have people share them. So they can just share all of their Remedy watches and you just like, you would end up just doing this at the top of your program and then never think about it again, right? I think that would be like an awesome feature, and unlike the stupid crap, like Visual Studio makes you write a plugin that you have to install, and it's like, there's already an executable. Like, you've loaded my executable. Why do I have to build a plugin, right? It makes no sense, but it's like, that's where their head is at. They're often, you know, we don't know how computer works land, so whatever. So I don't know how achievable that is, but that seemed to me like the shortest path towards a really baller watch window. And you wouldn't even have to then do most additional features. Because that watch context could even pass like parameters. Like, you know, you got like the string thing in there where you do like string count. Those could be things that get passed to this watch thing too. So the watch struct can just add things onto the bottom over time. And, you know, old stuff would still work because it doesn't need, if it doesn't ever touch lower down, it won't break, right? So you just keep adding stuff to that struct, and it's just like a giant context you hand to the thing. They fill it out, and back it comes, and now you're, you know, you're in Baller Town, right? So I don't know. That seemed really simple. I wanted to throw it out there because I was holding off on suggestions like that because, you know, Remedy was kind of just like getting started and adding like the basic features, but Remedy's getting to the point now where it has all the basic features, so I thought now might be a good time to think about, like, what's the easiest way to add, like, features that are just baller? They have nothing to do with basic debugging. They're more like, hey, this is cool, and most debuggers don't even have this, right? Anyway, that's all. Okay, so let me go ahead and try to figure out what the heck is going on here. But I do think that that's a problem, again, because we're never going to maybe get out of that split. I guess it is kind of hard to say, like, whether we will or won't. But yeah. All right, hold on a second. Okay, so taking a look now if I'm in the, like, bad part. So let me take a look at what those box bounds are. And you can see why I'm, like, motivated for that feature, because, like, I just want the box bounds to show, like, these three values, and then the dimension, so the subtraction of those values, right? And that's a really easy piece of code for me to write in my thing, but it'd be really hard for you to add that, because you'd need to have, like, a scripting language or something that, like, let me tell you what I want to see, and some of those things have to be expressions, and it's just, like, it just doesn't seem like a good path to go down. like having a scripting language and a debugger, because you've already loaded my actual code. So calling my code seems like the easiest way, because then the debugger don't have to do nothing, you know? So anyway, so in the box bounds here, where we've got like these values, I guess the answer is we're not splitting because why? Tell me why. I guess because some of these are just right on top of each other. Yeah. So I guess the answer there, and I'm not sure if this is the right answer or not, but I guess the answer there is like if it gets down to a degenerate case where you cannot split, then I guess what we do is just treat that as a leaf, right? So, so I guess like, where's my split kitty? Here it is. So I guess what we would do is like try to do this thing first. And if the count on either side is equal to the source, then we just don't split. Right? So I think it's this. So we'd come through here and we'd try to do this. We would see whether or not we could do anything about it. If we can't do anything about it, then meaning if this split doesn't work. So if we'd say like if positive count is less than source count and negative count is less than source count. So if we're always passing a lower source, then we do this. If we can't, right, then we're gonna set the KD index backwards, right? So we're gonna say, hey, bail, this is now a leaf, right? And so it'll change those. Now, we don't want to actually add this thing until then. So I would say that this stuff actually only happens like in here at that point. And so we have the ability to bail if the actual split procedure fails. How does that work? Wait, weren't we supposed to stop somewhere? Well, I guess that succeeded then. Okay, so now I'm assuming we're gonna have the problem of now we gotta debug our actual like raycast routine, and that's fine. So let's take a look at that. Okay. So here we're going to push this onto the stack, the start side bit, and here we're going to load out the packed value, right? And we're going to do the next split. And we're splitting. And here we're doing an actual leaf. Okay. So this says it had to check the other side as well. What's the stack depth at this point? 7. So I'm just going to watch what happens here. So it's sort of working. Let me run it for a while and just see. Whoa. Access violation writing location. Really? Hold on a second. So this does not bode well, like I said. So I'm assuming there's a bug in there, or we really screwed up somehow. Because even in debug mode, that first raycast pass should not take anywhere near this long, right? So what's going on here? If I do a break, we're in here. The depth is only 4. Weird. Are we just oscillating, perhaps? Maybe we just hit a loop here where we oscillate. It looks like that's exactly what's happening. But let's verify that. I mean, it's hard to say. I should probably print out the log. Also, I'm kind of curious, how many of these did we make? Not very many. So even if we were to walk them all, so our walk must be screwed up, right? Because even if we were to walk all of these things, then you wouldn't be able to spend this long testing them, right? It's just not, I don't think it's theoretically feasible. Let's see whether or not we get caught in an infinite loop by going into a build that probably could test everything if it wanted to. So let's do a release mode. So it does complete. So it's just like a very bad walk, I guess. And it doesn't produce a similar result, although I guess we don't really know for sure because we do have error in the system in general. But yeah, so like it seems really bad. I mean, I'm assuming that it shouldn't be that bad no matter how we ended up doing it. It shouldn't be as horrible as that, right? So I'm not sure. I'm not sure. We'll see. So let's see. I think we're almost done. We've got about 15 minutes left. So I guess we'll just try to do a little debugging here, and then next weekend we'll try to actually get to the bottom of everything. So yeah, that just takes... That's just really weird. All right, so let me also check to make sure that this finishes in a reasonable amount of time if I actually turn on debug mode in terms of that initial first one, because I'm assuming that it does, but I actually guess I don't know. So I'm going to go into debug mode, and I'm going to make sure that that initial thing should complete in a reasonable amount of time, right? Yeah. So we should expect that, roughly. We shouldn't expect our routine to be that much worse than it couldn't, get at least that far. So let's take a look. What's the problem? And again, we don't really know if the tree is built properly, so we may want to actually go through and work out by hand to what extent the tree makes sense. But Uh, if we take a look at the new routine, you can see us doing the testing here. And again, that's producing the T-ray stuff, which is what we actually need it to produce, right? And then we're doing the testing on the KD tree as we go down. And yeah, we just know whether we need to test the other side by using whether we get on the other side of the plane D, right? So I suppose one thing we could test is just to see how long this thing takes, assuming that we only ever go all the way down one side. And that would just look like this, right? And we would expect that to be basically instant, right? And it like totally isn't. So it seems really weird. Because that doesn't have to do like anything, right? It's only going to descend down like the briefest set of things. And then it's going to like be done. Like it shouldn't. I don't know why it would be having that, why it would take that long. Hmm. Hmm. I'm just trying to avoid starting a full debug pass on this thing because we don't have time to actually do it. So I'm thinking we gotta wait till next weekend. But it's like, yeah. I mean, something seems really wrong here. So let's take a look at some of these count values. So is it possible for me to just get that information out? So like, this should tell me, right? We have a thing that tests the walk. I want to say. So if we look at, I just want to see like how many of these things were tested. So it says like that well, I guess we don't record partitions, so we should do that, right? So total leaves tested is here, but partitions tested isn't. So we need like this here to do the partition test, right? Okay. So yeah, I just don't really know. So let's take a look at what these numbers compare to be. So if I set the lighting to use the old KD, what do those numbers look like versus the new one? So, I mean, the answer here is that the number of leaves is wicked high, right? Because this is how many leaves were tested with the new system. This is how many leaves were tested with the old system. And we're not even doing the walk. So something is really broken there, possibly because of the way that we're actually doing the dividing. It could just be that our tree is that bad. Right? So I don't know. So let's take a look and see what happens if we try to upgrade this a little bit. Right? Where we just spend more time building the split box, and we see if we can do better than this super, super, super crappy version. Because since now this one actually has to divide the boxes up and put them on either side, it creates a constraint that the tree build has to actually not be super sucky. So maybe what we'll do is say, okay, if we take and do this check the same way that we're doing it down here. So we're going to do this, right? We're going to do this. I don't actually know why we're bothering with this, because we don't need that, right? So this code is just doing count A, count B. Like, that's all this thing needs to do, right? And this doesn't need to be there at all. So all we need to do is sweep through here and see, like, using the classifier, the exact same thing we were doing before to see what would happen in these cases. And then we'll just pick the lowest min value, right? So we'll say... So when we come through here, we'll say that if count A, or I should say min count equals min, count A, count B, right? And then we'll say if the min count here is less than the lowest min count, or I should say if the lowest min count is greater than the min count, then we'll say that the lowest min count equals the min count. And we'll take it. Right? So this is how we'll pick our class. We'll say whichever one is, I'm sorry, maximum. So whichever count is higher, we'll take that. And what we want to do is minimize our maximum count. Right? So it's just a min-max tree at that point. And I don't think that's going to do it because I think we've got other bugs, but, you know, we'll find out, right? So, we'll see. Assuming that, was that a release build? Yeah, it was. Darn. I was like, if that wasn't a release build, then that was actually improvement, but it's not. So at this point, I might want to actually start printing out the tree as well, just so we can see what the tree looks like. At least the top bounds of it, maybe. I could also try dumping out the, like... Well, yeah, I don't know. Let's take a look at HH Lightprof and see what the total box count and stuff is after we're done. So here's the box count before we do it, right? Or is that after? Does that include ones we add? Or not? Well, we add those in though, right? So wait, why isn't that number higher than... Right, because we add box storage here. And like, what's going on? Something's weird here. So if we look at what the total box count is, it's not different, really. And you know what I might want to do too is make these printouts more labeled. So what I might want to do is say, like, in here, let me label which one we're doing. So before we go anywhere further in here, we'll just do like so here we'll just say, look, if we're using the old KD, we'll say old. If we're using the new KD, we'll say new. That way we can see which one we are in really easy in the printout, right? So here I can say like, okay, that's the new one. And then I can go ahead and switch it to the old one. But something's not adding up here. We've got a pretty obvious bug happening, and we just got to go fix that. Probably an index bug, just like I said at the beginning of the stream. So if you look at these two, right, here's the old one and here's the new one. So we didn't add that many more leaves, though, is the thing. So if we didn't add that many more leaves, why are we testing so many more leaves? How is that possible? Like, it shouldn't be possible. Because the leaves always have to be contiguous. So it's not like any given node can only refer to one set of leaves. So we've got a problem. Something's busted in the way that we're pulling out the leaf labels, right? Because it should not be possible to test that many more leaves using only a walk down one side of the tree. How is that possible? Something's up. Yeah, I'm not seeing it. I'm not seeing it. I mean, here's another example, right? So let's just see. If we just nerf this entirely. So now we are literally only doing the first run down the tree. How many leaves are we testing? So that's the old one. Let's switch to the new one. I mean, isn't that just so broken? Like, something is so... I'm totally at a loss to explain what's going on here. How on earth could you possibly test 5 million leaf nodes, so which is 10 times more than the old algorithm, without ever doing a tree walk? You're only testing one node at that point, right? Because the very first time you ever test any leaves at all, you exit the loop. What's going on? This is like impossible. Like this should not even be remotely possible to do what we're seeing. It should be actually impossible, right? So let's watch what happens, because I'm totally at a loss to explain that. Let's look at the first time through. Here's us walking down, right? And we walk down to a depth of whatever. We're going to test some leaves. I guess to be fair, there's a lot of them. Way too many. So I think our splitter is still totally busted, right? So I mean, one answer is like somehow we really just have that many leaves in this tree. In that many leaves in the one node. Yeah, and then we exit. So the answer is there's really just that many. So 43, testing 43 leaves. It's kind of nuts that testing only 43 leaves per raycast is still so slow, right? But it is. So how did we end up in a situation where there were 43 leaves we couldn't split? I mean, how is that possible? It doesn't seem likely. You know, right? It seems like our split KD is just really bad or something. So we come through here, we say, look, we're going to pick a splitter, and it's going to be the centroid of, you know, the boxes we all added up. And then we're going to go through and, oops, that's the wrong one. Yeah, so we're going to move through here. We're going to say, all right, if the box max is greater than the class distance, then the count for A goes up. If the box min is less than the class distance, then count B goes up, and whichever the larger the two is, if that is less than the best we have, we record it, right? So then we go in through here, and maybe this code is busted and just isn't ever working. So then we come through and we say, all right, let's add these. We say, okay, let's build a rect min max for the box we're looking at. Let's see if the maximum is on the other side of the plane D. Or if the minimum's on the other side. Sort them and record the bounds, which seems like what you would want. If we were able to split at all, so if anybody went on one side or the other, then we record the split. Otherwise, we don't. I mean, is that really failing that often? Like, how is that possible? It just seems so not possible. I feel like we must be working with these boxes in an incorrect way. Because since we have like mostly boxes that are just like grids of boxes, how the heck could you not split them? They're not overlapping most of the time, right? Even if we have some places where there's two boxes on top of each other, that's two total boxes. Everything else should still be able to be separated that way. I guess since we probably want this to be like a equal to, in this case though, is one thing I would say. So like like we don't actually need this to be a less than, right? We'll consider that to be not necessary to test, I would think, right? I mean, it's possible that would lead to cracks in the lighting. So it's a little bit hard to say. Like, maybe that's not what we want. Maybe we want, like, one side, the min side, or something to be a less than. And the box max side to be a less than or equal to. I don't really know. So I guess what I want to do now is look at that routine and just see what the heck it's doing. Not that. So what do we normally see? Like when we go through here the first time? Like what's our min count? Like what's our count A? What's our count B? And what's the source count? So that just looks, this looks totally fictitious. I mean, I guess this is actually dim index, which is 0. How is it possible that you're telling me that the maximum for the X value of these boxes is greater than or equal to a value, and the minimum is also less than that value for basically every box in the system? Like what? How are you arriving at that answer? That seems totally nuts. I mean, that's not possible. What am I missing here? So we're like totally off in La La Land. Are these box refs wrong? Like, are the box refs at this point just garbage? I mean, they look like they should be correct because here they are. So something is like really broken badly. And it's frustrating me that I can't tell what it is. So I'm just going to actually step through those comparisons. I'm like, it should be that I would immediately see that error, but I am like obviously so out to lunch today. It's a bad programming day. Apparently we've learned. You know, Anna sometimes says she has a bad drawing day and like nothing looks right. Well, it's a bad programming day because I don't see, like, this is obviously just totally wrong. And I'm not actually sure I know why. So here's the actual discriminator that we're looking at for these. So let's just put them up here. So here's our values. Here's our KD index, and here's our total bound center. So we're discriminate this thing for negative, like, all right, so even just that is ridiculous. Like, what the heck box is 35 units long in our system? What box is that? Is this because we changed the storage format and totally screwed it up somehow? Like, what are you talking about? And if so, why didn't the other one fail? So this is the place where we actually do this work, right? We loop through the boxes and we update the way that they're actually being recorded. So oops. Wait, no, that's okay. No, it's not. I don't need to oops that. So what's, yeah, I don't know. That just doesn't seem right. I'm going to keep running and just see is that how big most of these things are? What the heck? How are the max values of all these boxes the same? What is going on? So that's like it didn't do this transform, right? Like this transform is supposed to be the thing that changes it from the old position to the radius value. Why isn't that? Looks like it's not doing that, is what that looks like. Is the box count not set yet? No, it is. I'm going to step through this part, I guess. You see why I'm freaking out here, right? Yeah, I mean, we were getting those old values is what we were getting. Right? That's what we want to see. So why aren't we seeing that? Because we do this update, right? So that's going to run over all 1448 boxes. So how are we getting those values? How come they're wrong? Oops. So I'm going to take a look here and see what these now are set to. Yeah, so these are all set correctly. Well, I shouldn't say all, because I didn't actually get a chance to step through them. I tried to, but hit the wrong button. So these are all set correctly, so what the heck? Like, what am I seeing in there? Why was I seeing such weird values? And what is this? So what the heck? Like, what's box ref? Box ref is 0. I didn't think we were supposed to have a box 0, but I guess we do. All right, so if it is box 0, then what does that box look like? All right, so why were we seeing that weird KD index value? Because it's not... It's not what it said. So is this... Maybe this is just a remedy bug? Is that possible? Yes, maybe. Let's see. Yes. Okay. Okay, cool. All right, so it's just a remedy bug, actually. There's a bug in remedy with how to access off of the E value there, because if you actually put something in here that's... Oh no, it's not a remedy bug. It's my bug. Yay! So remedy helped me find my bug because that's a 3. That should not be a 3. Whew. Thank you, remedy. Remedy basically had the same bug, or I put code into... I asked remedy to evaluate the thing that I did wrong, and it was like, hey, I also did it wrong. And I'm like, yes. Awesome. So remedy was a debugger in a different way just then. It evaluated my bogus expression to the wrong thing, which is what you would get, and off we go. So that's good. All I needed to do was say this is dim index, not KD index here, and off we go. That was a cut and paste bug. I don't know if this will help us here. Hopefully it will to a certain extent, because now we've got rid of that obvious bug. Let's take a look at what it says. Yeah, so... I don't think this is probably going to get us out of the woods, because that was just one of probably many bugs that we have here. So a couple things, like I assume we're running in the nerfed mode now, and that's why this is so fast. But at least it is fast now, which is what it should have been. And the leaf count is like now down in a more reasonable range, and so on. All right, so we're getting there. I'm gonna stop debugging for today, and we'll start debugging later tomorrow. So if I just put this back in, I'll leave it this way, and then we can start debugging it next weekend. So here's what it would actually cost, which is expensive. So it still sucks, but at least now it sucks in a slightly different way. So at least now we can start to look at like the building of the tree and whether it makes sense, and then look at our actual runtime code and see if it's doing what we expect it to do. And then next weekend we can hopefully get through all that and make a judgment call on whether this is an improvement or not, right? Because we don't really know. But you can see how much worse it is here. So it's still running very poorly. It's just not as bad as it was previously. And I'm going to let this go so I can see what the TPL values are. Right? So we can kind of see what that breaks.